Welcome back to Scientific Discovery Hub, your gateway to the wonders of the universe. Have you ever wondered why some comets blaze like cosmic beacons while others remain stubbornly dim? This video dives into one of the most intriguing astronomical mysteries of recent years. Why C2025 R2 SWAN shone brightly at magnitude 4, while interstellar visitor 3I Atlas stayed faint, despite both making headlines in 2025. Buckle up as we unravel the science behind their contrasting glows, blending cutting-edge research with celestial storytelling. In this episode, we'll explore the cosmic luminosity equation, the delicate balance of distance, solar heating, and composition that determines a comet's brightness. You'll discover how SWAN's blistering close approach to the Sun, just 0.5 AU, supercharged its activity, while 3I Atlas's more distant Perihelion, 1.36 AU, left it starved for solar energy. But this isn't just about numbers. We'll journey to the edges of the cosmos to compare their origins, one born in our solar system's Oort Cloud, the other a billion-year-old relic from interstellar space. Get ready to unpack orbital chaos, from retrograde paths to meteor shower potential, and peer into the fragile hearts of comets, where SWAN's explosive outburst created a dazzling dust cloud, while 3I Atlas held its composure. We'll also decode chemical fingerprints that reveal SWAN's water-rich solar system roots versus 3I Atlas's alien CO2 and nickel, offering clues about their formation environments. And don't miss the role of solar elongation, the cosmic spotlight effect that made SWAN visible to backyard astronomers while hiding 3I Atlas behind the Sun. By the end, you'll see how these comets are more than fleeting spectacles. They're messengers of cosmic history, bridging our solar system to the wider galaxy. Whether you're a seasoned stargazer or new to astronomy, this video will deepen your appreciation for the forces shaping our night sky. Hit the subscribe button and enable notifications so you never miss a dive into the universe's greatest puzzles. And if you're hungry for more, check out our videos on asteroid impacts, exoplanet hunting, and the hunt for dark matter. The cosmos is full of stories. Let's explore them together. Now, let's ignite the engines of curiosity and embark on this stellar adventure. The universe is a vast tapestry of light and shadow, where celestial bodies dance to the rhythms of gravity and time. Among these wanderers, comets stand as ephemeral flames, born in the cold, dark reaches of space and ignited by the sun's warmth. Yet their brilliance is fleeting, dictated by forces both intimate and unfathomable. Why do some comets blaze so fiercely that they pierce the night sky with a ghostly glow, while others flicker and vanish into obscurity? The answer lies in a delicate cosmic equation, a balance of distance, solar heating, and composition. Consider two travelers. 1. C2025 R2 SWAN hurtles inward with a trajectory that brings it perilously close to the Sun, its icy heart melting into a radiant spectacle. Another, 3I Atlas, drifts through the inner solar system at a more modest pace, its glow subdued yet intriguing. What determines which comet becomes a beacon and which fades into the void? To unravel this mystery, we must peer into the mechanics of their existence, into the alchemy of ice, dust, and starlight that transforms them from silent wanderers into celestial fireworks. At the heart of a comet's luminosity is a process as ancient as the solar system itself, sublimation. Composed of frozen water, carbon dioxide, methane, and other volatile compounds, a comet's nucleus lies dormant until it ventures near the Sun. As solar radiation strikes the nucleus, its surface warms and the ices begin to vaporize directly into gas, bypassing the liquid phase. This sublimation releases fine particles of dust and gas, forming a glowing coma, a temporary atmosphere that can stretch thousands of kilometers. The expelled material reflects sunlight, scattering it back into the cosmos as a visible trail. The brightness of this phenomenon depends on three key variables: the comet's proximity to the Sun, perihelion distance, the size and composition of its nucleus, and the efficiency of its activity, how rapidly it sheds material. Take C2025 R2 SWAN, for instance. Its perihelion distance of 0.5 AU places it within the innermost reaches of the solar system, closer to the Sun than Mercury. At this distance, solar radiation bombards the nucleus with intensity, accelerating sublimation and triggering explosive outbursts. The comet's rapid brightening from magnitude 11 to 6.9 in mere weeks attests to its vigorous activity, a symphony of ice and dust unleashed under extreme heat. Conversely, 3I Atlas, with a perihelion of 1.36 AU, experiences milder solar influence. Though still within the domain of the terrestrial planets, its slower heating rate limits the scale of its outgassing, resulting in a more subdued glow. The contrast between these two comets illustrates a fundamental truth. The closer a comet ventures to the Sun, the more violently it reacts, transforming into a brilliant but transient beacon. Yet proximity alone cannot fully explain a comet's luminosity. The nucleus's size and composition play equally critical roles. AMPA's larger nucleus harbors more volatiles, sustaining prolonged activity as it journeys through the inner solar system. Conversely, smaller nuclei burn out quickly, their reserves of ice exhausted in days or weeks. Composition matters too. Comets rich in carbon dioxide or methane may exhibit more dramatic outbursts than those dominated by water ice, as these substances sublimate at lower temperatures. Additionally, the efficiency of activity, how effectively a comet converts solar energy into ejected material, varies dramatically. Some nuclei are riddled with fissures and vents, allowing gas and dust to escape freely, while others remain stubbornly inert. These factors combine in a cosmic calculus, determining whether a comet becomes a dazzling spectacle or a faint smudge against the stellar backdrop. This luminosity equation reveals why comets are nature's most unpredictable fireworks. Their brilliance is fleeting, a brief but spectacular interplay of physics and chance, yet it also raises profound questions. Why does C2025 R2 SWAN surge in brightness so suddenly, only to risk disintegration? Why does 3I Atlas, an interstellar traveler, emit a fainter glow despite carrying exotic chemical signatures? The answers lie not merely in their current paths, but in their origins, a journey that spans eons and galaxies. For C2025 R2 SWAN, its violent outbursts hint at a fragile constitution. The comet's nucleus, likely fractured by tidal forces or internal pressure, may be on the brink of collapse. Such disintegration is not uncommon among comets that venture too close to the Sun. The SWAN instrument aboard SOHO has captured countless examples of comets crumbling as they approach perihelion, their remnants dispersing into clouds of dust and gas. The fact that C2025 R2 SWAN briefly peaks at magnitude 6.9 before fading, or perhaps vanishing entirely, underscores the precariousness of its existence. Its luminous arc is a final act, a fleeting performance in the cosmic theater. By contrast, 3I Atlas tells a story of interstellar solitude. Born in the distant reaches of another star system, it carries the chemical fingerprints of its alien home. Spectroscopic analyses reveal a nucleus rich in carbon dioxide and water ice, with traces of cyanide and nickel substances rarely found in equal measure in solar system comets. These anomalies suggest that 3I Atlas's parent star system may have formed under conditions vastly different from our own. Its hyperbolic trajectory, with an eccentricity of 6.141, confirms that it will never return to the solar system. It is a solitary messenger, bearing secrets of a galaxy-wide history. The implications of these discoveries ripple outward. Comets like C2025 R2 SWAN and 3I Atlas serve as cosmic probes, revealing the diversity of environments in which planetary systems form. They remind us that the solar system is not an isolated oasis, but a node in a vast network of stellar nurseries. The fact that 3I Atlas may be older than the solar system itself, possibly originating from the Milky Way's thick disk, challenges our understanding of interstellar dynamics. If such ancient comets can traverse the galaxy undisturbed, what other relics of primordial chaos await discovery? To decode the fates of these comets, we must look beyond their immediate journeys and consider the grander architecture of the cosmos. The origins of C2025 R2 SWAN are rooted in the Oort Cloud, a distant reservoir of icy bodies shaped by the gravitational tides of the solar system. 3I Atlas, however, hails from interstellar space, a relic of a star system long since dissolved. In the next segment, we will trace the cosmic pathways that brought these two comets to our doorstep, one from the depths of the solar system, the other from the infinite expanse beyond. Through their stories, we glimpse the interconnected web of matter and motion that binds the universe together. In the vast, silent expanse of the universe, comets emerge as ethereal wanderers, fleeting spectacles that whisper tales of distant star systems and ancient solar neighborhoods. These icy relics, born in the cold fringes of space, traverse the heavens with tales of glowing gas and dust, their paths illuminated by the sun's fierce embrace. To gaze at a comet is to witness a cosmic ballet choreographed over millennia, where the gravitational pull of stars and planets dictates the dance steps of these celestial vagabonds. Yet beyond their beauty lies a deeper mystery. Do comets hail from the familiar cradle of our solar system, or do they arrive as interstellar visitors from realms we've never charted? This question anchors our exploration of two extraordinary comets, C2025 F2, SWAN, a disintegrating wanderer from the outer reaches of our solar system, and 3I Atlas, a hyperbolic interloper from the uncharted depths of interstellar space. Their stories are not merely astronomical phenomena, but windows into the origins of our universe itself. While C2025 F2 traces its roots to the Oort Cloud, a hypothetical reservoir of icy bodies at the solar system's edge, 3I Atlas defies such boundaries, its trajectory revealing it as a traveler from a star system far removed from our own. Together, these comets embody the duality of cosmic existence, the known and the unknown, the ancient and the eternal. To understand their significance, we must first unravel the threads of their origins. What forces birth these comets? What secrets do their compositions and orbits hold? And how do their fates, whether disintegration or escape, reflect the dynamic interplay of gravity, time, and chance? As we embark on this journey, we are reminded that every comet is a message in a bottle adrift in the cosmic sea, carrying clues to the architecture of the universe and our place within it. Comets are time capsules, their frozen nuclei preserving materials from the earliest epochs of their birthplaces. For C2025 F2 SWAN, this origin lies within the solar system. Discovered in late March 2025 by the Solar and Heliospheric Observatories (SOHO) SWAN instrument, the comet followed a nearly parabolic orbit, suggesting it had traveled from the Oort Cloud, a theoretical shell of icy objects extending up to 100,000 AU from the Sun. Calculations indicate that C2025 F2 spent the last 40,000 years hurtling toward the inner solar system, its journey initiated by a perturbation from a passing star, or the gravitational tug of the Milky Way's tidal forces. Yet 3I Atlas tells a different tale. Its discovery in July 2025 by the Atlas Survey Telescope marked a historic moment. It became the third interstellar object ever identified in our solar system, joining the enigmatic 1I Oumuamua and 2I Borisov. Unlike its solar system-bound counterparts, 3I Atlas followed an unbound hyperbolic trajectory with an orbital eccentricity of 6.1414, the highest of any known interstellar object. This trajectory, combined with its hyperbolic excess velocity of 58 km per second, proved irrefutable evidence of its extraterrestrial origin. Tracing its path backward in time, astronomers determined that 3I Atlas hailed from the direction of the Milky Way's thick disk, a region populated by ancient stars. Based on its motion and the kinematics of the galactic disk, estimates suggest the comet could be between 3 and 14 billion years old, older than the solar system itself. These two comets exemplify the stark contrast between intra- and interstellar origins. C2025 F2, bound to the Sun's gravity, represents the remnants of our own cosmic nursery, its nucleus forged from the same primordial material that birthed the planets. Conversely, 3I Atlas arrives as a stranger, its ice and dust shaped by the chemistry of a distant star system. The differences extend beyond their orbits. While C2025 F2's Coma likely contained water ice, 3I Atlas's Coma was found to be rich in carbon dioxide, a signature of an environment where temperatures and pressures differ from those in our solar system. Such distinctions underscore the diversity of planetary systems across the galaxy, offering tantalizing hints about the conditions that govern the formation of comets and life beyond Earth. The study of comets like C2025 F2 and 3I Atlas transcends mere observation. It is a voyage into the fabric of cosmic history. For C2025 F2, Its disintegration in mid-April 2025 serves as a poignant reminder of the fragility of these ancient travelers. As the comet neared Perihelion, its closest approach to the Sun, it succumbed to the relentless heat, its nucleus shattering and releasing a final burst of brilliance before fading into a diffuse cloud of dust. This event aligns with the life cycle of many Oort Cloud comets, which, after eons of isolation, are occasionally nudged into the inner solar system by gravitational perturbations. Their demise, though tragic, provides critical insights into the internal structure of comets. Did C-2025 F2's nucleus contain volatile ices that vaporized under solar radiation, or was its disintegration triggered by structural weaknesses inherent to its formation? These questions drive the search for understanding the processes that govern the evolution of icy bodies in the solar system. Meanwhile, 3I Atlas challenges our assumptions about interstellar objects. Unlike its predecessor 2I Borisov, which exhibited a coma rich in water, 3I Atlas's coma was dominated by carbon dioxide and carried traces of cyanide and nickel elements that suggest a unique chemical history. These findings raise profound questions. Is CO2 the dominant volatile in the birthplaces of interstellar comets, or is this a quirk of 3I Atlas's specific origin? Could such differences in composition reflect variations in the protoplanetary disks of other star systems? Or do they hint at the existence of multiple mechanisms for comet formation in the galaxy? Furthermore, 3I Atlas's extreme age, if indeed it predates the solar system, implies that it has spent eons traversing the Milky Way, surviving encounters with countless stars and nebulae. How has its structure endured such a journey? Does its survival suggest that interstellar comets are more resilient than previously thought? Or is 3I Atlas an anomaly among cosmic nomads? The implications of these comets extend beyond their individual stories. They serve as probes of the solar system's boundaries, testing theories of planet formation and galactic dynamics. For instance, the fact that 3I Atlas originated from the thick disk, a region associated with older metal-poor stars, challenges models that assume interstellar objects predominantly hail from young star-forming regions. Similarly, the discovery of C-2025 F2's nearly parabolic orbit reinforces the idea that the Oort Cloud is a dynamic reservoir, constantly replenished by gravitational interactions. Together, these comets illuminate the interconnectedness of the cosmos, reminding us that the solar system is not an isolated island, but a node in a vast interwoven web of celestial phenomena. Understanding the origins of comets is merely the first step in deciphering their cosmic journeys. Equally vital is the study of their orbits, those invisible threads that bind them to the gravitational symphony of the universe. For C-2025 F2 and 3I Atlas, these orbits dictate their fates, one spiraling toward disintegration, the other escaping into the interstellar void. But how do these trajectories shape the comet's luminosity and visibility to Earth-based observers? How do the laws of physics transform an icy nucleus into a glowing spectacle in the night sky? To answer these questions, we must delve into the mechanics of cometary motion. Amper's comet's brightness depends not only on its size and composition, but also on its proximity to the Sun and Earth. C-2025 F2, for example, reached a peak magnitude of 5 in early May 2025, briefly becoming visible to the naked eye. Yet its sudden disintegration in April 2025 underscores the delicate balance between solar heating and structural integrity. In contrast, 3I Atlas, despite its interstellar speed, will never rival the brilliance of a typical solar system comet. Its faintness, even at perihelion, highlights the challenges of observing interstellar objects and raises intriguing questions about the nature of their activity. Why does 3I Atlas emit so much CO2, a gas with a higher sublimation temperature than water ice? Could this hint at a different evolutionary path for interstellar comets, one shaped by the harsher environments of distant star systems? As we turn our focus to the physics of cometary orbits, we uncover a universe governed by elegant mathematical principles. The parabolic and hyperbolic trajectories of C-2025 F2 and 3I Atlas are not random. They are the inevitable consequences of energy and momentum conserved over eons. These paths reveal the unseen forces at play, the gravitational tugs of planets, the drag of solar wind, and the subtle perturbations from passing stars. By tracing these orbits, we gain not only insight into the comets themselves, but also into the broader architecture of the cosmos. Thus, the story of comets is far from complete. Their origins, orbits, and eventual fates are chapters in a grander narrative, one that spans the birth of stars, the evolution of galaxies, and the search for life beyond Earth. In the next segment, we will explore how the dance of gravity and light shapes these icy travelers, transforming them from silent wanderers into radiant beacons of cosmic wonder. Word count: 3,000, approximately. Note: the script adheres to the structure of introduction, explanation, 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 and transition, weaving scientific detail with a contemplative tone. Each section expands on the referenced comet's origins, implications, and cosmic significance, while maintaining a narrative flow that emphasizes the wonder of the universe. In the vast silent expanse of the cosmos, where time stretches into eternity and space folds into the unknown, comets emerge as fleeting spectacles, messengers from the frozen outskirts of the solar system and beyond. They arrive like silent travelers, their icy nuclei trailing luminous veils of gas and dust, each one a whisper from a distant past, a story etched in stardust. Among the countless celestial bodies that drift through the heavens, comets hold a special place in human imagination and scientific inquiry. Their periodic appearances, their unpredictable brilliance, and their origins in the coldest, darkest corners of the universe make them both enigmatic and deeply significant. This narrative explores three remarkable comets: C2025 F2, SWAN, 3I Atlas, and C2025 R2, SWAN. Each of these comets represents a unique chapter in the grand cosmic drama. C2025 F2 SWAN, discovered in the ethereal glow of the Solar and Heliospheric Observatory's SWAN camera, traces a parabolic path that brings it perilously close to the Sun, where solar radiation triggers a dramatic transformation. Its journey ends in disintegration, a testament to the fragility of celestial bodies under the Sun's relentless gaze. Then there is 3I Atlas, an interstellar wanderer hailing from the depths of the Milky Way, with a hyperbolic trajectory and a velocity far exceeding the gravitational grip of the solar system. It offers a rare glimpse into the chemistry and origins of objects born in distant stellar nurseries. Lastly, C2025 R2, SWAN, emerges as a paradox, a comet that briefly becomes visible to the naked eye, defying expectations as it approaches Perihelion and potentially Earth. Together, these comets illuminate the dynamic and often chaotic nature of the cosmos, reminding us that even in the vast emptiness of space, life and death unfold in cycles as ancient as the universe itself. To understand these comets is to peer into the mechanisms that govern the solar system and the galaxy. Their orbits, compositions, and interactions with the Sun reveal fundamental truths about the forces that shape celestial motion and the materials that build planets. Yet beyond their scientific value, comets inspire awe. They are fleeting reminders of the universe's indifference and grandeur, of the delicate balance between creation and destruction that defines existence. As we follow the trajectories of C2025 F2 SWAN, 3I Atlas, and C2025 R2 SWAN, we embark on a journey through time and space, unraveling the mysteries of their origins and fates while contemplating our own place in the cosmic tapestry. Comets are more than mere rocks adrift in the void. They are dynamic entities shaped by the invisible forces of the cosmos. At their core lies a fragile nucleus of ice, dust, and organic compounds, remnants of the primordial material that coalesced to form the solar system. As a comet ventures inward from the frigid outer reaches, the Sun's rays begin to work their alchemy. Solar radiation heats the nucleus, causing volatile ices such as water, carbon dioxide, and methane to sublimate directly into gas. This process creates a glowing coma, a tenuous envelope of gas and dust that surrounds the nucleus, and a tail that streams away from the Sun, sculpted by solar wind and radiation pressure. The transformation is both violent and beautiful, a celestial metamorphosis driven by the interplay of heat, light, and gravity. The behavior of a comet is inextricably linked to its orbital path, a trajectory dictated by the gravitational dance between the Sun and the planets. Comets can follow highly elliptical orbits, bringing them to perihelion, the point of closest approach to the Sun at varying distances. The closer a comet comes to the Sun, the more intense the solar heating becomes, accelerating sublimation and activity. For C2025 F2 SWAN, its perihelion at 0.333 AU places it within the orbit of Mercury, a realm of searing temperatures and extreme solar influence. Here, the nucleus is subjected to forces that can fracture its structure, triggering explosive outbursts and eventual disintegration. In contrast, 3I Atlas's perihelion at 1.36 AU, nestled between Earth and Mars, offers a relatively safer vantage point. While still subject to solar heating, the comet avoids the Sun's most violent extremes, preserving its integrity as it continues its interstellar voyage. The distinction between elliptical and hyperbolic orbits further shapes a comet's destiny. Elliptical orbits, with eccentricities less than 1, indicate a periodic return to the inner solar system, as seen in comets like Halley's. However, many comets originate from the distant Oort Cloud, a spherical shell of icy bodies extending up to 100,000 AU from the Sun. Gravitational perturbations from passing stars or giant molecular clouds can nudge these objects into the inner solar system, where their orbits become highly elliptical or even hyperbolic. Hyperbolic orbits, defined by eccentricities greater than 1, signify that an object is not gravitationally bound to the Sun and will escape the solar system after its encounter. 3I Atlas exemplifies this fate, hurtling through the solar system at a velocity of 58 kilometers per second, over twice that of 2I Borisov, and destined to vanish into the interstellar abyss. Such comets serve as ambassadors from the galaxy, carrying clues about the conditions of their birthplaces and the processes that shape them. Understanding a comet's orbit requires precise measurements of its position and velocity over time. Observations from ground-based telescopes and space-based instruments like the Solar and Heliospheric Observatory (SOHO) and the James Webb Space Telescope (JWST) provide critical data for C2025 F2 SWAN. Its nearly parabolic orbit suggests an 80,000-year journey from a distance of 3,750 AU, a journey that ended in disintegration. In contrast, 3I Atlas's hyperbolic trajectory, traced back to the direction of the galactic center, hints at an age of billions of years, far predating the solar system itself. These orbital histories are not merely academic exercises. They are windows into the past, revealing the forces that govern the motions of celestial bodies and the origins of the universe's most elusive visitors. Yet, even the most carefully charted orbit is subject to the whims of chance. Gravitational interactions with planets can alter a comet's path, sometimes sending it into a more direct collision course with the Sun, or redirecting it toward the outer solar system. For C2025 R2 SWAN, its orbit intersects Earth's path, raising the possibility of a meteor shower as debris from the comet's nucleus collides with our atmosphere. Such events underscore the interconnectedness of the solar system, where the fates of comets and planets are intertwined in a cosmic ballet. The study of these interactions is not only a pursuit of knowledge, but also a necessity for planetary defense, ensuring that humanity remains vigilant against potential hazards from above. Through the lens of orbital mechanics, comets emerge as both fragile and resilient. They are vulnerable to the Sun's fury, yet capable of enduring millennia-long journeys across the galaxy. Their stories, inscribed in the language of physics and chemistry, offer profound insights into the workings of the universe. As we trace the trajectories of C2025 F2 SWAN, 3I Atlas, and C2025 R2 SWAN, we are reminded that the cosmos is a place of constant motion and transformation, where every orbit tells a tale of creation, destruction, and rebirth. The disintegration of C2025 F2 SWAN serves as a poignant reminder of the delicate balance that sustains cometary bodies. Discovered in the ethereal glow of the Solar and Heliospheric Observatory's SOHO SWAN camera, this comet's journey was marked by a rapid ascent in brightness, followed by an abrupt decline. Initially detected at a magnitude of 11, in late March 2025, C2025 F2 SWAN brightened steadily as it approached perihelion, reaching magnitude 8.6 by mid-April. However, its luminosity plateaued and then waned, signaling the onset of structural failure. By 22 April, the nucleus had vanished entirely, leaving behind a diffuse cloud of dust and gas. The disintegration was likely triggered by the immense thermal stresses experienced at perihelion. where the sun's radiant energy exceeded the cohesive strength of the comet's icy matrix. This phenomenon is not uncommon among comets that venture too close to the sun. The sublimation of volatile ices generates internal pressures that can fracture the nucleus, leading to fragmentation and eventual dissipation. The fate of C2025 F2 SWAN underscores the transient nature of comets, which are often described as cosmic snowballs, composed of a mixture of ice, dust, and organic molecules. The composition of a comet's nucleus plays a crucial role in determining its resilience to solar heating. Volatile ices such as water, carbon dioxide, and ammonia sublimate readily, while more refractory materials like silicates and carbonaceous compounds offer some degree of structural integrity. In the case of C2025 F2 SWAN, the rapid brightening observed in April 2025 suggests a sudden release of volatiles, possibly due to the exposure of fresh ice layers following a prior fragmentation event. The subsequent fading indicates that the remaining fragments lack sufficient cohesion to sustain prolonged activity, a stark contrast to the more robust nuclei of comets like 67P, Churyumov, Gerasimenko, which survived multiple perihelion passages during its 6.5-year orbital cycle, while C2025 F2 SWAN met its end in the sun's embrace. 3I Atlas offers a different perspective on cometary survival. As the third interstellar object ever discovered, 3I Atlas hails from a distant stellar system, its origin traced back to the direction of the Milky Way's galactic center. Unlike native solar system comets, which originate from the Oort Cloud or the Kuiper Belt, 3I Atlas carries a unique chemical signature shaped by the conditions of its birthplace. Observations by the James Webb Space Telescope, JWST, and the Hubble Space Telescope have revealed an unusually high concentration of carbon dioxide in its coma, alongside traces of water ice, water vapor, carbon monoxide, and carbonyl sulfide. These findings challenge existing models of cometary composition, suggesting that interstellar comets may differ significantly from their solar system counterparts in terms of volatile content and structural properties. The survival of 3I Atlas through its perihelion passage at 1.36 AU is a testament to its resilience. At this distance, solar heating is intense enough to drive sublimation and activity, but not so extreme as to induce catastrophic fragmentation. The comet's hyperbolic trajectory, with an orbital eccentricity of 6.141, ensures that it will escape the solar system after its encounter, carrying with it the secrets of its interstellar origins. The fact that 3I Atlas remains intact despite its high-speed journey through the solar system raises intriguing questions about the nature of its nucleus. Is it composed of denser, more cohesive materials compared to native comets? Or does its unusual chemical composition provide additional stability against thermal stresses? These questions highlight the importance of studying interstellar comets, which serve as cosmic probes of distant planetary systems and the conditions that prevail in the interstellar medium. The discovery of 3I Atlas also has profound implications for our understanding of the distribution of interstellar objects in the galaxy. Prior to its detection, only two interstellar objects, 1I Oumuamua and 2I Borisov, had been identified, both originating from directions near the solar apex, the point in the sky toward which the sun is moving, relative to the local stellar neighborhood. 3I Atlas, however, hails from the southern celestial hemisphere, a direction opposite to the solar apex, challenging assumptions about the symmetry of interstellar object arrivals. This discrepancy suggests that interstellar objects may originate from a variety of galactic environments, including the thick disk, a population of older stars with distinct kinematic and chemical properties. If confirmed, this finding would necessitate a revision of current models of interstellar object delivery, emphasizing the role of galactic dynamics in shaping the flux of these objects through the solar system. The study of 3I Atlas also sheds light on the age of interstellar comets. By analyzing the vertical component of its hyperbolic excess velocity, Watts + 18.5 kilometers per second, astronomers have inferred that 3I Atlas likely belongs to the thick disk population, implying an age of 7.6 to 14 billion years. This estimate, derived from the typical lifetimes of thick disk stars, suggests that 3I Atlas predates the solar system by several billion years, making it one of the oldest comets ever observed. Such an ancient origin raises fascinating possibilities about the conditions that prevailed in the early universe and the processes that gave rise to the first planetary systems. Did 3I Atlas form in a different galactic environment, perhaps in a now-defunct star-forming region? Or was it ejected from its home system during a chaotic early phase of planetary evolution? These questions remain unanswered, but the continued observation of 3I Atlas as it departs the solar system promises to yield new insights into the nature of interstellar comets and their role in the broader galactic context. In contrast to the ephemeral fate of C2025 F2 SWAN and the interstellar provenance of 3I Atlas, C2025 R2 SWAN presents a compelling case of cometary unpredictability. Discovered in September 2025 at a magnitude of 7.4, this comet rapidly brightened to peak at 6.2, becoming visible in binoculars from the southern hemisphere. Its perihelion at 0.5 AU places it within the orbit of Venus, a distance that subjects it to intense solar heating and the potential for dramatic outbursts. The comet's trajectory also brings it close to Earth, with a projected closest approach of 0.26 AU in October 2025, raising the possibility of a meteor shower as debris from its nucleus enters Earth's atmosphere. The intersection of its orbit with Earth's path highlights the dynamic interplay between comets and planets, a reminder that the solar system is not a static entity, but a living, evolving system where celestial bodies constantly interact. The study of C2025 R2 SWAN also underscores the challenges inherent in predicting cometary behavior. Unlike C2025 F2 SWAN, whose disintegration was relatively straightforward, C2025 R2 SWAN exhibits erratic fluctuations in brightness, a phenomenon attributed to the uneven distribution of volatile ices on its surface. As certain areas of the nucleus are exposed to solar radiation, they sublimate rapidly, creating localized jets of gas and dust that can temporarily enhance the comet's luminosity. However, these outbursts are often followed by periods of dimming, as the exposed volatiles are depleted, leaving behind a dormant surface until the next exposure. This cyclical pattern of activity complicates efforts to model the comet's evolution and assess its long-term survival. Will C2025 R2 SWAN endure its perihelion passage, or will it follow the path of C2025 F2 SWAN and succumb to the sun's relentless pull? Only time and continued observation will tell. Through the stories of C2025 F2 SWAN, 3I Atlas and C2025 R2 SWAN, we gain a deeper appreciation for the diversity and complexity of comets. They are not merely passive wanderers, but active participants in the cosmic drama, shaped by the forces of gravity, radiation, and chance. Whether they disintegrate in the sun's glare, escape into the interstellar void, or defy expectations with their resilience, comets remind us that the universe is a place of constant transformation, where even the smallest and most fragile bodies play a role in the grand tapestry of existence. As we continue to observe and study these celestial messengers, we not only expand our knowledge of the solar system and the galaxy, but also reaffirm our connection to the cosmos, a connection forged in the same stardust that gives rise to comets, planets, and life itself. The disintegration of C2025 F2 SWAN and the survival of 3I Atlas raise a fundamental question. What determines a comet's fate when it ventures into the sun's domain? The answer lies in the delicate architecture of its nucleus, a structure composed of ice, dust, and organic compounds held together by weak gravitational and electrostatic forces. Unlike the rocky bodies of asteroids or the gaseous giants of the outer planets, comets are inherently fragile, their cohesion dependent on the intricate balance between internal pressures and external forces. As a comet approaches perihelion, the sun's radiant energy initiates a cascade of physical and chemical changes that can either reinforce or dismantle its structure. The heart of this process is sublimation, the direct transition of volatile ices from solid to gas without passing through a liquid phase. Water, carbon dioxide, and other volatiles embedded within the nucleus begin to sublimate as solar radiation penetrates the surface, creating pockets of pressurized gas that can destabilize the surrounding material. If the internal pressure exceeds the mechanical strength of the nucleus, the comet may fracture, releasing fragments that continue along their own trajectories. In some cases, These fragments may persist as smaller comets, maintaining their activity as they orbit the Sun, while in others the nucleus may disintegrate entirely, leaving behind a diffuse cloud of dust and gas. The fate of C-2025 F2 SWAN exemplifies this process. Its rapid brightening, followed by a sudden fade, suggesting a catastrophic disruption that rendered its nucleus unable to sustain further activity. However, the survival of 3I Atlas indicates that not all comets succumb to this fate. Its hyperbolic trajectory and perihelion distance of 1.36 AU provide a margin of safety against the most extreme effects of solar heating, allowing it to retain its structural integrity as it traverses the inner solar system. The composition of its nucleus may also play a role in its resilience. The presence of carbon dioxide and other refractory materials, as detected by the James Webb Space Telescope, suggests that 3I Atlas possesses a more stable internal structure compared to native solar system comets, which are often dominated by water ice. These differences may reflect the unique conditions of its interstellar origin, where the availability of volatile materials and the intensity of stellar radiation could have influenced the formation of its nucleus in ways that differ from those of comets born in the Oort Cloud. Beyond the immediate effects of solar heating, the long-term survival of a comet depends on its orbital history and the gravitational influences it encounters. Comets that originate from the distant Oort Cloud often experience long elliptical journeys that bring them close to the Sun only once every few thousand years, minimizing the cumulative effects of sublimation and structural degradation. In contrast, comets with shorter orbital periods may undergo repeated perihelion passages, each one eroding their surfaces and reducing their overall mass. Some comets, like 67P Churyumov-Gerasimenko, survive multiple returns by shedding material in a gradual manner, while others, like C-2025 F2 SWAN, meet their demise in a single dramatic encounter. The study of these variations provides insight into the evolutionary pathways of comets and the factors that govern their longevity. As we turn our attention to the internal dynamics of comets, we find ourselves at the threshold of a deeper exploration, one that delves into the molecular and atomic processes that govern their behavior. What unseen forces drive the sublimation of ices and the release of gases? How do the compositions of cometary nuclei vary across the solar system and beyond? And what can these variations tell us about the origins of comets and the environments in which they formed? These questions lie at the heart of the next segment, where we will examine the intricate chemistry of cometary nuclei and the role they play in shaping the evolution of the solar system. By unraveling the mysteries of cometary interiors, we not only advance our understanding of these enigmatic bodies, but also shed light on the broader processes that have shaped the universe since its inception. In the vast, uncharted expanse of the cosmos, where time stretches into epochs and distances blur into abstraction, comets emerge as fleeting spectacles of ice and fire. These interstellar wanderers, born in the frigid outskirts of star systems, trace arcs across the heavens, their fragile hearts glowing briefly before vanishing into the void. Among them, C-2025 F2 SWAN stands as a poignant example of cosmic impermanence. Discovered in late March 2025 by the watchful eyes of the Solar and Heliospheric Observatory's SWAN instrument, this comet was poised to become a binocular marvel, its icy nucleus warming under the Sun's gaze. Yet by mid-April, its brightening stilled, and its luminous coma dissolved into a shroud of dust, a silent testament to the fragility of its core. In stark contrast, 3I Atlas, an interstellar traveler from the Milky Way's depths, hurtled through the inner solar system with a robust heart, its volatile gases erupting in a steady, controlled rhythm. What distinguishes these two tales? What forces govern the delicate balance between a comet's survival and its demise? To answer, we must peer into the crucible of a comet's nucleus, where the line between brilliance and oblivion is as thin as the frost on its surface. The universe is replete with such paradoxes. Comets are both ancient and ephemeral, their origins stretching back to the birth of stars, yet their lifetimes measured in mere centuries. They are messengers, bearing secrets of the cold dark beyond, yet they are also ephemeral artists, painting the sky with tales of gas and dust, before crumbling into stardust. The story of SWAN and 3I Atlas is not merely a chronicle of two celestial bodies, but a meditation on the duality of existence, the tension between creation and destruction, permanence and transience. As we unravel their fates, we glimpse the grandeur of the cosmos and the humility of our own fleeting place within it. Comets are not merely icy rocks adrift in space. They are time capsules of volatile compounds, held together by gravity and the fragile grip of frozen water, carbon dioxide, and methane. When a comet approaches the sun, the heat triggers a process called sublimation, where ice is transformed directly into gas without becoming liquid. This outgassing lifts dust and debris from the nucleus, forming the luminous coma and the sweeping tail that define a comet's ethereal beauty. Yet this process is inherently destabilizing. The uneven heating of a comet's surface can create fractures, while the release of volatile gases exerts internal pressure, threatening to tear the nucleus apart. C 2025 F2 SWAN succumbed to this instability. Observed in early April with a magnitude of 10.6, it displayed a faint tail of 10 arc minutes, a sign of active sublimation. By April 5, a sudden outburst boosted its brightness to magnitude 8.6, with a tail stretching 2 degrees across the sky. Such outbursts often signal the onset of disintegration. For SWAN, the event proved fatal. By late April, its nucleus had vanished, leaving behind a diffuse cloud of dust. The SWAN instrument aboard SOHO, designed to map the solar wind in Lyman alpha radiation, had first glimpsed the comet on March 29 at a distance of 0.92 AU from the Sun. Over the following weeks, amateur astronomers tracked its erratic behavior, noting how its coma swelled and contracted like a dying heartbeat. The final act was a quiet dissolution, a reminder that even the brightest stars can fade. 3i Atlas, by contrast, bore the Sun's touch with resilience. Discovered in July 2025 by the Atlas survey in Chile, this interstellar comet approached from the galactic center, its hyperbolic trajectory betraying its origin beyond our solar system. With a velocity of 58 kilometers per second, far exceeding the escape velocity of the Sun, it would never return. Yet, unlike SWAN, its nucleus endured. Observations by the James Webb Space Telescope revealed a coma rich in carbon dioxide and carbon monoxide, gases that sublimate at lower temperatures than water ice. This chemical composition allowed 3i Atlas to shed material steadily, avoiding the catastrophic ruptures that befell SWAN. The Hubble Space Telescope captured its nucleus at less than 5.6 kilometers in diameter, a modest size that paradoxically enhanced its stability. Smaller nuclei lacked the structural complexity to fracture under stress, instead eroding uniformly. The difference in their fates lies in the dance of volatility and structure. SWAN's nucleus, likely composed of a mix of water ice and rocky debris, fractured under the strain of rapid sublimation. 3i Atlas, with its CO2-driven activity and compact form, maintained equilibrium. Their stories underscore a universal truth. Fragility and resilience are not fixed traits but outcomes of context, chemistry, and chance. To witness a comet's disintegration is to confront the essence of impermanence. Comets, like all things in the universe, are subject to the laws of entropy, the gradual dispersal of order into chaos. Yet, in their brief moments of radiance, they embody the sublime. The disintegration of SWAN in April 2025 was not merely an astronomical event, but a philosophical parable. Its nucleus, a fragile architecture of ice and rock, could not withstand the relentless pull of the Sun. The outburst that marked its peak brightness was both a climax and an elegy, a final flourish before dissolving into dust. In this, SWAN mirrors the human condition, a delicate construct of matter and memory, destined to erode with time. Yet even in demise, comets leave legacies. The dust trails they scatter become part of the interplanetary medium, seeding the void with the raw materials of new worlds. When SWAN's fragments crossed Earth's orbit in October 2025, they may have ignited a meteor shower, a celestial fireworks display born from its ashes. Such is the cycle of cosmic rebirth. Similarly, 3i Atlas's journey through the inner solar system offered a rare glimpse into the chemistry of interstellar space. Its coma, enriched with carbon monoxide and nickel, hinted at the conditions of its birthplace, a star system long dead, yet its legacy carried forward in the comet's flight. The contrast between SWAN and 3i Atlas invites reflection on the nature of existence. SWAN's fragility reminds us that beauty is often ephemeral, a fleeting burst of light against the darkness. 3i Atlas's endurance, however, speaks to the resilience of life in its myriad forms. Just as the comet's nucleus withstood the sun's fury, so too do living organisms adapt to survive in hostile environments. Both narratives, though vastly different, converge on a single truth. The universe is a tapestry woven from the threads of creation and decay, where every ending births a new beginning. Moreover, these comets serve as cosmic diplomats, bridging the chasm between the known and the unknown. 3i Atlas, with its interstellar origins, carries whispers of alien worlds, its trajectory a record of the Milky Way's turbulent history. Its high orbital eccentricity, 6.141, the highest among interstellar objects, suggests it hails from the galaxy's thick disk, a population of ancient stars older than the solar system itself. In studying 3i Atlas, we are not merely observing a comet. We are deciphering a message from a civilization of stars, a relic of a time before Earth existed. Meanwhile, SWAN's fate underscores the precariousness of existence. Its disintegration, though tragic, was not in vain. The data gathered by observatories like SOHO and the Lowell Discovery Telescope illuminated the processes that govern cometary evolution. The fact that SWAN's nucleus completely disappeared by April 22, yet its fragments briefly flared to magnitude 9.3, highlights the complexity of cometary dynamics. Each fragment, a tiny world unto itself, followed its own path, some scattering into the void, others destined to collide with planets in millennia to come. In this sense, even a disintegrating comet becomes a progenitor of futures, its legacy encoded in the trajectories of its remnants. These stories, etched in light and shadow, remind us that the cosmos is not a static realm, but a dynamic theater of transformation. Comets, with their dual roles as destroyers and creators, encapsulate this duality. They arrive from the cold dark, their icy hearts glowing briefly before returning to the void, carrying with them the seeds of new worlds and the echoes of ancient stars. In their rise and fall, we find a mirror for our own lives, a reminder that to exist is to be part of an eternal cycle, where nothing is lost, only transformed. Even as SWAN's nucleus crumbled into stardust, and 3i Atlas departed the solar system on a path that will never return, their legacies endure. The dust trails they left behind will linger in the interplanetary medium, invisible to the naked eye yet integral to the cosmic ecosystem. These particles, forged in the crucibles of their respective nuclei, may one day coalesce into new asteroids or enrich the atmospheres of distant planets. In this way, the disintegration of a comet is not an end but a metamorphosis, a redistribution of matter that fuels the universe's endless reinvention. Yet the story does not conclude here. For every comet that fades, another is born in the outer reaches of the solar system, waiting for the sun's call. The Oort Cloud, a hypothetical reservoir of icy bodies extending trillions of kilometers from the sun, teems with such dormant worlds, some perturbed by the gravitational tugs of passing stars or molecular clouds, will one day embark on journeys toward the inner solar system, repeating the cycle of brilliance and disintegration. Whether they survive or perish depends on the same cosmic lottery that governs SWAN and 3i Atlas. As we turn our gaze to the future, the lessons of these comets linger. They challenge us to embrace both the fragility and resilience of existence, to find wonder in the transient and meaning in the inevitable. For in the dance of comets, we see a reflection of the universe itself, a realm where creation and destruction are not opposites, but partners in an eternal waltz. And as long as there are eyes to watch the sky and minds to ponder its mysteries, the hearts of comets will continue to beat in the silent infinite dark. In the boundless expanse of the universe, where time stretches into epochs and distances dwarf comprehension, comets emerge as transient messengers. These icy wanderers, born of ancient chaos and stardust, trace arcs through the void, whispering secrets of the cosmos to those who dare to look up. Among the countless stars, 3 comets have recently graced the heavens, each a fleeting masterpiece of light and shadow, a testament to the dynamic interplay of forces that govern our corner of the galaxy. The year 2025 has become a chapter in humanity's celestial diary, marked by the arrivals of C2025 F2 Nice C. Their stories intertwine with the fabric of the universe, revealing not only the fragility of their icy hearts, but also the resilience of their journeys across interstellar realms. To observe these comets is to witness the raw poetry of physics, the dance of gravity, the sublimation of frozen worlds, and the radiant glow of dust scattering starlight. Yet their paths are not merely scientific curiosities. They are threads in the tapestry of cosmic history, each carrying echoes of distant stars and forgotten epochs. See 2025 F2. Born in the outer reaches of the solar system, disintegrated under the sun's gaze, its remnants scattering like stardust across the sky. 3I Atlas, an interstellar traveler from a realm beyond our own, raced through the solar system at velocities exceeding 58 kilometers per second, its carbon dioxide-rich coma painting a ghostly silhouette against the void. And C 2025 R2, discovered mere days after its closest approach to the Sun, offered a fleeting glimpse into the mechanics of coma formation and the delicate balance between survival and destruction. These comets are not isolated phenomena. They are part of a grander narrative, one that spans the birth of galaxies, the collision of stars, and the quiet evolution of worlds. To understand them is to glimpse the universe's heartbeat, pulsing through the vacuum in the language of light and motion. The story of C 2025 F2 SWAN began in late March 2025, when its icy nucleus was first glimpsed in images captured by the Solar and Heliospheric Observatory (SOHO). Discovered by astronomers Vladimir Bezugli, Michael Matiasso, and Rob Matson, the comet was initially a faint smudge of light, its magnitude hovering around 11. By early April, its brightness surged, and observers noted a coma spanning 2 arc minutes, with a tail stretching up to 2 degrees. Yet this crescendo was short-lived. By mid-April, the comet's brightness stalled, and by 22 April, its nucleus had vanished entirely, leaving behind a tenuous cloud of dust. C 2025 F2's fate was sealed by the Sun's relentless pull. Its orbit, calculated to have an approximate 80,000-year period, brought it perilously close to the inner solar system, skimming within 0.333 AU of the Sun, just 49.8 million kilometers from the star's blinding heat. At this distance, the comet's fragile structure could not withstand the thermal stresses. Volatiles sublimated violently, and the nucleus fractured, its remnants dispersing into a luminous haze. The disintegration was not sudden, but a gradual unraveling, with fragments briefly flaring to magnitude 9.3 before fading into obscurity. This comet's journey underscores a fundamental truth. Comets are ephemeral. Born in the cold depths of the Kuiper Belt, or Oort Cloud, they are fragile relics of the solar system's infancy. When nudged by gravitational perturbations or passing stars, they spiral inward, their icy cores destined to evaporate or shatter under the sun's glare. C 2025 F2's brief brilliance was a final act of defiance, a reminder that even the most fleeting phenomena can leave indelible marks on the cosmos. In stark contrast to C 2025 F2's tragic end, 3I Atlas C 2025 N1 arrived as an interstellar nomad, a visitor from beyond the solar system, discovered on 1 July 2025 by the Atlas Survey Telescope in Chile. This comet hurtled through space at a velocity of 58 kilometers per second, over twice the speed of the previous interstellar object, 2I Borisov. Its hyperbolic trajectory, with an orbital eccentricity of 6.14, betrayed its origins. It had never been bound to the Sun, and it would never return. 3I Atlas's origin story is as enigmatic as its journey. Tracing its path backward in time, astronomers determined it emerged from the direction of the Milky Way's thick disk, a region populated by ancient stars older than the solar system itself. With an estimated age of 7 to 14 billion years, this comet predates our planetary neighborhood by eons. Its chemical composition offers tantalizing clues about its birthplace. Rich in carbon dioxide and water ice, with traces of cyanide and nickel, 3I Atlas carries the fingerprints of a stellar nursery, unlike any in our own backyard. Despite its interstellar provenance, 3I Atlas's interaction with the solar system was brief. It passed Perihelion on 29 October 2025, at a distance of 1.36 AU, skimming between Earth and Mars. Yet, even at this relatively close approach, the comet remained a faint speck, its peak magnitude capped at 11.5. Observations by the Hubble and James Webb Space Telescopes revealed a nucleus smaller than 5.6 kilometers in diameter, its coma dominated by dust and volatile gases. Unlike the sun grazers of the solar system, 3I Atlas's activity was driven by the sublimation of carbon dioxide and methane, not water ice. Its trajectory, tilted 175° relative to the ecliptic, ensured it would escape undisturbed. By December 2025, it will have departed the inner solar system, its final bow a silent farewell to a realm it never called home. The third comet of 2025, C2025 R2 SWAN, emerged as a sudden burst of light in September 2025. Its discovery by Vladimir Bezugli via SOHO's SWAN instrument marking a rare triumph of serendipity. Detected just days after its perihelion passage on 12 September, the comet had already reached a peak magnitude of 6.2, its tail stretching 2 degrees across the sky. From the southern hemisphere, it hung near Spica, visible to the naked eye in binoculars as a ghostly smudge. What made C2025 R2 remarkable was its rapid evolution. Between August and September 2025, its brightness increased from magnitude 11 to 6.9, a transformation fueled by a violent outburst of volatiles. Observers speculated that the comet's nucleus, likely a fragile amalgamation of ice and rock, had fractured under the sun's heat, releasing a torrent of dust. By 19 October, it would reach its closest approach to Earth at 0.26 AU, a mere 39 million kilometers, and potentially trigger a meteor shower as its debris intersected Earth's orbit. C2025 R2's orbit remains a mystery, its aphelion estimated at 250 to 1000 AU. Whether it will return in millennia or vanish forever depends on the precise details of its trajectory, a riddle yet unsolved. Yet its brief, brilliant display serves as a reminder of the universe's capacity for both chaos and beauty. The disparity in brightness among these comets reveals the intricate artistry of dust and coma formation. C2025 F2 SWAN's disintegration amplified its dust output, creating a coma that reflected sunlight like a cosmic mirror. Its tail, spanning 2 degrees, was a testament to the power of fragmentation, each shard of ice and rock scattering photons in a luminous cascade. In contrast, 3I Atlas's coma, though rich in volatile gases, remained compact and faint. Its carbon dioxide and cyanide emissions, detectable only by instruments like Hubble, hinted at a chemistry alien to the solar system. The size and composition of a comet's dust grains dictate its visibility. Larger particles scatter light more efficiently, creating the diffuse halos we see in comas, like those of C2025 F2. Smaller grains, however, are more susceptible to solar radiation pressure, often forming tails that stretch across the sky. C2025 R2's rapid brightening was likely due to a sudden release of fine dust, a transient eruption that transformed it from a faint smudge to a visible object in just weeks. These variations underscore a deeper truth. Comets are not uniform entities. Their appearances are shaped by the volatile mix of ices and silicates they carry, the intensity of solar heating, and the fragility of their nuclei. To study them is to decode the recipe of the early universe, where the building blocks of life may have formed in the frosty crucibles of protoplanetary disks. The arrival of 3I Atlas raises profound questions about the frequency and origins of interstellar objects. While 1I Oumuamua and 2I Borisov hinted at the existence of such visitors, 3I Atlas's trajectory and composition suggest a new paradigm. Its southern origin, contrary to early predictions that interstellar objects would predominantly arrive from the solar apex, challenges assumptions about the distribution of rogue comets and asteroids in the galaxy. Moreover, 3I Atlas's age, potentially exceeding 7 billion years, places it in a category of its own. If it hails from the Milky Way's thick disk, a population of stars older and more metal-poor than our own, it may carry materials forged in the primordial fireballs of ancient supernovae. Its carbon dioxide-rich coma, unlike the water-dominated comas of solar system comets, hints at a different evolutionary path, perhaps one shaped by the harsher environments of its birthplace. Studying 3I Atlas is akin to peering into a parallel universe. Its brief visit offers a rare opportunity to compare the chemistry and dynamics of distant star systems with our own. What processes sculpted its nucleus? Did it originate in a binary star system, where gravitational tugs could hurl objects into interstellar space? Or was it ejected from a young planetary system, much like the hypothesized origin of our own Oort Cloud? These questions linger like the comet's faint tail, dissolving into the void, yet echoing in the minds of scientists. The disintegration of C2025 F2, SWAN, and the fleeting brilliance of C2025 R2 highlight the paradox of cometary survival. Most comets endure only a handful of perihelion passages before their volatile cores erode, yet their very fragility makes them invaluable. Each disintegration releases a trove of data, spectral signatures of their ices, the dynamics of their fragmentation, the behavior of their dust in solar winds. For C2025 F2, its demise was a spectacle of cosmic theater. The outburst observed on 5 April 2025, followed by the nucleus's disappearance, provided a textbook case of how thermal stress and rotational instability can dismantle a comet. The resulting dust cloud, glowing faintly for weeks, served as a natural laboratory for studying particle dynamics in microgravity. Similarly, C2025 R2's sudden brightening offered insights into the mechanisms of outbursts, whether triggered by internal pressure, impacts, or the sudden exposure of fresh ices. As 2025 draws to a close, the legacies of C2025 F2 3I Atlas and C2025 R2 linger in the annals of astronomical history. Yet their stories are far from over. The data they left behind, the spectral lines of carbon dioxide, the trajectories of their dust clouds, the echoes of their disintegrations, will fuel generations of research. Future missions, such as the upcoming Interstellar Mapping and Acceleration Probe IMAP, may one day intercept the faint traces of 3I Atlas as it sails toward the galaxy's edge. Meanwhile, simulations of C2025 R2's orbit may reveal whether it will return in millennia or vanish into the cosmic deep. But beyond the science lies a deeper truth. Comets are reminders of our place in the cosmos. They are the children of stellar nurseries, the refugees of distant systems, and the architects of change in the solar system. To watch them is to witness the universe's duality, the delicate and the violent, the finite and the infinite. As we turn our eyes skyward, we are not merely observers, but participants in a grand dialogue, one written in light and carried on the winds of time. The next chapter awaits. Perhaps in the coming decades, a new comet will streak across the sky, its story unfolding in real time. Until then, we hold the tales of 2025 in our hands, a mosaic of dust and wonder, a testament to the endless curiosity that binds us to the stars. In the vast, silent expanse of space, comets trace luminous arcs through the darkness, their glowing tails shimmering like distant memories of ancient wanderings. Yet despite their brilliance, these cosmic travelers often remain hidden from human eyes, obscured by the very star they orbit, the Sun. The key to unlocking their visibility lies in a subtle geometric relationship, solar elongation. This angle formed between the Sun and a comet as seen from Earth dictates whether a comet becomes a fleeting spectacle or remains forever unseen. For some comets, this alignment places them high in the twilight sky, offering a rare opportunity for observation. For others, it condemns them to vanish behind the sun's blinding glare, their stories told only by the instruments that dare to peer beyond the limits of human sight. Understanding solar elongation is essential for unraveling the mysteries of comets, as it governs not only their visibility but also the challenges faced by those who seek to witness their passage. Through the lens of this celestial dance, we begin to grasp the delicate balance between light and shadow, between discovery and obscurity. Solar elongation is more than a numerical value. It is the silent arbiter of a comet's fate in the night sky, defined as the angular distance between the Sun and a comet as viewed from Earth. This measurement determines how easily a comet can be observed. When a comet reaches a sufficient elongation, typically more than 20 degrees from the Sun's glare, it becomes visible to ground-based observers, rising above the horizon as the Sun sets or descending before it rises. The greater the elongation, the longer the window of opportunity for observation. However, for many comets, this moment is fleeting, as their trajectories carry them ever closer to the Sun, reducing their elongation and forcing them into the sunlit realm, where human vision falters. Consider the case of C2025 R2, SWAN, which reached an elongation of 30 degrees in September 2025. This favorable positioning allowed the comet to be glimpsed in the southern hemisphere's twilight sky, its brightness peaking at magnitude 6.2, an object easily visible through binoculars. Its elongation granted it a brief but significant window of accessibility, enabling amateur astronomers and casual stargazers alike to witness its passage. In contrast, 3I Atlas followed a much more elusive path. As it approached perihelion in October 2025, its trajectory carried it directly into solar conjunction, where its solar elongation dropped below 30 degrees, rendering it invisible to Earth-based observers. While this might seem like an unfortunate twist of fate, it also underscored the intricate choreography of celestial mechanics, where the positions of planets, comets, and the Sun must align just right for a glimpse of cosmic beauty. For those who seek to observe comets, solar elongation presents a paradox. The closer a comet comes to the Sun, the more brilliant it may become, but the more difficult it is to see. This delicate balance between brightness and visibility shapes the experience of every observer, from seasoned astronomers to curious stargazers. Ampere's comet that reaches perihelion, its closest point to the Sun, often undergoes a dramatic transformation, its icy nucleus heating and releasing gas and dust that form a luminous coma and tail. Yet this very brilliance is frequently accompanied by an unfavorable elongation, placing the comet in direct sunlight where human eyes and even advanced telescopes struggle to detect it against the overwhelming glare. The challenge is compounded by the fact that comets do not follow predictable paths. Their orbits are often highly elliptical, and their behavior can change unpredictably as they interact with the solar wind and gravitational forces. This is where the tools of modern astronomy become indispensable. When a comet such as 3I Atlas enters solar conjunction, Earth-based observations become impossible. But robotic instruments aboard spacecraft like those orbiting Mars or monitoring the Sun offer a chance to capture its evolution. In the case of 3I Atlas, its passage near Mars at a distance of just 0.19 AU in October 2025 meant that orbiters such as NASA's Mars Reconnaissance Orbiter and the European Space Agency's Mars Express could potentially observe the comet as it neared perihelion. These missions, designed to study the red planet, became unwitting witnesses to an interstellar visitor's fleeting journey through the inner solar system. Meanwhile, ground-based telescopes in the southern hemisphere, equipped with adaptive optics and sensitive detectors, continued to track C2025 R2 SWAN as it remained favorably positioned for observation. The observer's dilemma, therefore, is not merely one of patience and timing, but also of ingenuity, as astronomers must deploy a diverse array of instruments and techniques to piece together the full story of a comet's passage. The theater of the cosmos is vast and unforgiving, where the interplay of light, distance, and perspective determines what we can observe and what remains hidden. Comets, in their erratic and often unpredictable journeys, remind us that the universe does not always conform to the expectations of human observers. Their visibility hinges on a complex interplay of factors: orbital mechanics, solar radiation, and atmospheric conditions, each influencing how and when we can witness their passage. For instance, the elongation of a comet dictates its position in the sky relative to the Sun, but it is the sensitivity of our instruments that ultimately allows us to detect it. Even a comet with a modest brightness can become a target of interest if its elongation is favorable, while an intrinsically luminous comet may go unnoticed if it is lost in the Sun's glare. This duality underscores the importance of technological advancement in expanding our observational reach. In the case of C2025 R2 SWAN, its elongation of 30 degrees placed it in a sweet spot for southern hemisphere observers, where it became a binocular object with a visible tail spanning 2 degrees. This visibility was not accidental, but the result of precise orbital dynamics and a fortuitous alignment. Conversely, 3I Atlas's trajectory brought it dangerously close to the Sun, necessitating the use of specialized instruments capable of operating in extreme conditions. The James Webb Space Telescope, with its infrared capabilities, played a crucial role in studying 3I Atlas's composition, revealing the presence of carbon dioxide and water ice despite the comet's faintness. Similarly, the Hubble Space Telescope provided high-resolution images that help constrain the comet's nucleus size, illustrating how these instruments act as extensions of our senses, allowing us to perceive phenomena beyond the limits of natural vision. The observer's dilemma, therefore, is not solely a matter of waiting for the right moment, but also of harnessing the power of technology to pierce through the veil of cosmic obscurity. Beyond the immediate challenges of visibility, the study of comets is deeply intertwined with the legacy of observation itself. Every discovery, every recorded passage, adds to the tapestry of human understanding, weaving together the threads of history, science, and curiosity. The act of observing a comet is not merely a technical endeavor. It is a continuation of an ancient tradition, one that stretches back to the earliest records of celestial events, etched into stone and parchment. From the Babylonians who charted the movements of the heavens, to the modern astronomers who employ cutting-edge instruments, the pursuit of cometary knowledge has always been a testament to humanity's desire to comprehend the universe. The elongation of a comet, while a scientific metric, carries with it the weight of this collective effort, reminding us that each observation is a link in a chain that connects past and present. Consider the role of citizen scientists and amateur astronomers in this grand narrative. For C 2025 R2 SWAN, the initial discovery by Vladimir Bezugli, through the Solar and Heliospheric Observatory's SWAN instrument, was followed by contributions from a global network of enthusiasts who refined its orbit and tracked its evolution. These individuals, equipped with nothing more than their passion and basic equipment, often serve as the first line of detection, their efforts complementing those of professional observatories. In the case of 3i Atlas, amateur astronomers like Sam Dean played a pivotal role in uncovering pre-discovery images that confirmed the comet's interstellar origin. Such collaborations highlight the democratization of astronomical discovery, where the boundaries between professional and amateur blur in the shared pursuit of knowledge. The observer's dilemma, then, is not only about the physical limitations of our instruments, but also about the enduring human spirit that seeks to overcome them, ensuring that no comet, no matter how elusive, remains entirely hidden from our gaze. While solar elongation governs the visibility of comets, their true cosmic significance lies in the chemical signatures they carry, messages from the distant reaches of the universe, written in the languages of ice, gas, and dust. Comets are not merely wandering rocks of frozen debris. They are time capsules, preserving the primordial materials that coalesced in the early days of the solar system and beyond. When a comet approaches the sun, its surface warms, releasing volatile compounds that form a glowing coma and trailing tail. These emissions, analyzed through spectroscopy and remote sensing, reveal the elemental and molecular composition of the comet, offering insights into its origins and evolutionary history. For interstellar comets like 3i Atlas, this information is particularly profound, as it provides a glimpse into the chemistry of distant star systems, far removed from the familiar environment of our own cosmic neighborhood. The James Webb Space Telescope's observations of 3i Atlas uncovered an abundance of carbon dioxide, a finding that distinguishes it from many solar system comets, which typically contain higher proportions of water ice. This unusual composition suggests that 3i Atlas may have formed in a different kind of protoplanetary disk, one where temperatures were low enough to allow carbon dioxide to condense, but insufficient for water to freeze. Such conditions could exist in the outer regions of other planetary systems, where the chemistry of forming bodies differs significantly from that of our own. Additionally, the detection of cyanide and atomic nickel in 3i Atlas's Coma hints at a complex history of thermal processing and chemical interactions, further enriching our understanding of the diversity of cometary materials across the galaxy. These discoveries are not just scientific milestones. They are echoes of cosmic events that occurred billions of years ago, carried across interstellar space and delivered to our doorstep. As we decode these messages, we begin to appreciate the interconnectedness of the universe, where the building blocks of life and planetary systems may share a common heritage stretching far beyond the confines of our solar system. In the vast silent expanse of the cosmos, comets drift like ancient messengers, their tails glowing with the secrets of distant stars and forgotten epochs. These icy wanderers are more than fleeting spectacles in the night sky. They are cosmic time capsules, preserving the raw materials of planetary systems long before our own sun ignited. Among them, two comets stand out. 3i Atlas, an interstellar traveler bearing the signature of a foreign star system, and SWAN's latest discovery, C 2025 R2, a relic of our own solar system's tumultuous youth. Their chemical compositions, etched by the hands of time and the crucibles of stellar nurseries, offer a glimpse into the hidden histories of their birthplaces. What do these molecular fingerprints tell us? How do they bridge the chasm between our familiar corner of the Milky Way and the infinite tapestry of the universe? To answer these questions, we must peer into the hearts of these comets, where frozen gases and metallic whispers speak of worlds unseen. Comets are not merely rocks cloaked in ice. They are laboratories of chemistry, forged in the cold void between stars or the chaotic dance of protoplanetary disks. When sunlight warms their surfaces, they exhale clouds of volatile compounds, water, carbon dioxide, methane, and even traces of heavy metals like nickel. These emissions are not random. They are the echoes of their origins, encoded in the ratios of elements and isotopes. For 3I Atlas, its abundance of carbon dioxide and cyanide gas marks it as a child of a distant frigid system, where ices form under conditions alien to our own. Meanwhile, the water-rich Coma of C2025 R2 mirrors the chemistry of comets born in the outer reaches of our solar system, where the sun's feeble warmth once sculpted icy bodies into cosmic sculptures. Together, these comets paint a picture of a universe teeming with diversity, where the building blocks of life and planets are scattered like stardust across the void. To unravel their stories is to trace the threads of cosmic history. Every atom in their tails, every molecule in their comas, carries a message from the past, a message that demands to be deciphered. As we embark on this journey, we will not only uncover the secrets of these two comets, but also confront the profound question: are we alone in the universe? Or are we part of a grand interconnected web of matter and energy stretching across galaxies? Let us begin with 3I Atlas, the third interstellar comet ever discovered. Unlike the asteroids and comets that orbit the Sun, 3I Atlas hails from elsewhere in the galaxy. Its hyperbolic trajectory, revealing a birthplace far beyond our solar system's gravitational reach. Its journey began billions of years ago, perhaps in the cold, dark expanse of a distant star system's outer reaches. Here, temperatures hover near absolute zero, allowing volatile compounds like carbon dioxide and methane to freeze into solid ices. These ices, embedded in the comet's nucleus, are now exposed as the comet races toward the Sun, sublimating into gas and dust under the star's warming embrace. The James Webb Space Telescope's observations of 3I Atlas have unveiled a striking anomaly. Its coma is unusually rich in carbon dioxide, a molecule that requires extreme cold to condense. This suggests that 3I Atlas formed in a region where temperatures never rose above -200 degrees Celsius, far colder than the Kuiper Belt, the birthplace of many of our solar system's comets. Such an environment could exist in the outer disks of young star systems, where material is shielded from stellar radiation and remains in perpetual darkness. The presence of carbon dioxide also implies that the comet's parent star system experienced prolonged periods of stability, allowing ices to accumulate undisturbed over millions of years. Yet 3I Atlas is not a passive relic of its past. The Very Large Telescope has detected cyanide gas and atomic nickel vapor in its coma, elements typically associated with violent processes like shockwaves or high-energy collisions. Nickel, in particular, is a heavy metal often produced in the hearts of exploding stars or the molten cores of rocky planets. Its presence in 3I Atlas hints at a turbulent history. Perhaps the comet's nucleus was shattered by a cataclysmic event in its home system, scattering fragments into the void. These fragments, now warmed by the sun, release nickel atoms as their ices sublime, creating a ghostly glow in the infrared spectrum. This duality of pristine ices and shattered remnants paints a picture of a comet born in peace, but shaped by chaos. In contrast, C2025 R2 SWAN tells a different tale. Discovered by Vladimir Bezugli in the Solar and Heliospheric Observatory's SWAN instrument, this comet is a familiar face in our cosmic neighborhood. Its coma is dominated by water ice, a hallmark of comets originating in the outer solar system. When sunlight strikes its nucleus, water molecules break apart, releasing hydrogen and oxygen ions that interact with solar wind particles to create the comet's glowing iron tail. This process mirrors the behavior of Halley's Comet and countless others born in the Kuiper Belt or Oort Cloud. Yet C2025 R2's rapid brightening from magnitude 11 to 6.2 in mere weeks suggests a more dynamic history. Its tail, stretching 2 degrees across the sky, is not merely a trail of ice and dust, but a testament to the comet's resilience. What drives this sudden luminosity? Observations hint at a recent outburst, possibly triggered by the sudden release of trapped volatile gases beneath the nucleus's surface. Such events are common in comets like C2025 F2 SWAN, which disintegrated spectacularly in April 2025, leaving behind a swirling dust cloud. For C2025R2, the outburst may have exposed fresh layers of ice, amplifying its reflectivity and creating the illusion of a brighter, more vibrant body. Yet the comet's fate remains uncertain. Will it survive its close encounter with Earth in October 2025? Or will it follow the path of C2025F2, crumbling under the sun's relentless pull? Only time and continued observation will tell. Together, these comets exemplify the universe's capacity for both order and upheaval. 3I Atlas, with its alien chemistry, reminds us that the cosmos is a mosaic of diverse star systems, each contributing its unique fingerprint to the galactic tapestry. C2025R2, in turn, anchors us to our own history, a reminder that even within our solar system, change is inevitable. Their chemical signatures are not merely data points, but stories waiting to be read, written in the language of atoms and molecules. To study comets is to hold a mirror to the universe. 3I Atlas, with its interstellar origins, forces us to confront the vastness of our galaxy. Its carbon dioxide-rich Coma is a direct link to the conditions of its birthplace, a star system so distant that its light takes millennia to reach us. Yet here it is, hurtling through the inner solar system, its tail a fleeting beacon against the backdrop of eternity. What can we learn from such an object? First, its chemistry offers clues about the diversity of planetary systems. If 3I Atlas formed in a region where carbon dioxide dominates over water ice, as in our own solar system, does this imply that some star systems prioritize different volatile compounds in their formation? Or does it suggest that 3I Atlas's home is a colder, darker place, where even the faintest glimmers of starlight struggle to penetrate the void? The comet's age adds another layer of intrigue. Studies suggest that 3I Atlas may be 7 to 14 billion years old, predating the solar system itself. If true, it is a relic of an era when the Milky Way was young and chaotic, a time when stars collided and planetary systems were still in their infancy. Such an object is not just a visitor, it is a witness to the early universe, carrying imprints of conditions we can no longer observe directly. Its trajectory, aligned with the galactic thick disk, hints at a birthplace among ancient stars, their compositions enriched by generations of supernovae. In studying 3I Atlas, we are not merely analyzing a single comet. We are peering into the galactic past, reconstructing the environments that shaped entire civilizations of stars and planets. Meanwhile, C2025R2, SWAN, serves as a bridge between the cosmic and the intimate. While its chemistry is familiar, water ice, carbon monoxide, and traces of organic molecules, it is the comet's behavior that captivates. Its sudden outbursts and unpredictable brightness mirror the dynamic processes that once sculpted our own solar system. Billions of years ago, comets like C2025R2 may have delivered water and organic compounds to the young Earth, seeding the ingredients necessary for life. Today, as we watch its tail stretch across the southern hemisphere's skies, we are reminded of the same cosmic forces that gave rise to our oceans and atmosphere. The comet's journey from the distant Oort Cloud to its close encounter with Earth is a microcosm of the solar system's history, a reminder that even in the present, the past is alive and active. Yet both comets challenge our understanding of time and scale. 3I Atlas, older than the solar system, exists in a realm of deep time that defies human comprehension. Its passage through the inner solar system is a brief moment in its eternal voyage, a flash of brilliance in a 7 billion-year odyssey. In contrast, C2025R2's 1400-year orbital period, or perhaps 20,000, depending on future observations, places it on a timescale that stretches beyond recorded history. For humans, these durations are abstract concepts. For the comets themselves, they are the rhythm of existence. To observe them is to participate in a dialogue between the ephemeral and the eternal, a conversation that transcends species, culture, and even the boundaries of space-time. Moreover, the study of these comets reveals the interconnectedness of the universe. 3I Atlas's interstellar origin underscores that our solar system is not an isolated bubble, but a node in a vast network of stellar systems. Comets like this one are the messengers of this network, carrying material and information between stars. Similarly, C2025R2's chemistry reflects the shared heritage of all solar system bodies, a legacy of the same primordial cloud that gave birth to the sun, planets, and moons. These connections remind us that the universe is not a collection of isolated entities, but a symphony of interactions, where the fate of one star system ripples across the cosmos. As we continue to observe these comets, we must ask, what other secrets lie dormant in their nuclei? Could 3I Atlas harbor amino acids, or other complex molecules, evidence of prebiotic chemistry in an alien system? Might C2025 R2's disintegration in October 2025 reveal hidden layers of ice or exotic minerals? Each observation brings us closer to answering these questions, but the deeper truth remains. Comets are not just objects to be studied, they are living testaments to the universe's creativity and resilience. If comets are time capsules, then their chemical fingerprints are only the first page of a much larger story. Beyond the molecules they carry, comets are storytellers of time itself, chronicling the eons of their journeys through space. 3I Atlas, with its 7-billion-year-old nucleus, is a relic of an era when the Milky Way was young, its stars forming in frenzied bursts of creation. C2025 R2, though younger by comparison, still carries the weight of millennia, its orbit a spiral thread in the tapestry of the solar system's evolution. To understand these comets is to grasp not just their origins but their destinies, their trajectories through time as they traverse the void. But time is not merely a measure of duration. It is a lens through which we perceive the universe's grand design. The disintegration of C2025 F2 in April 2025, the sudden brightness of C2025 R2, the interstellar voyage of 3I Atlas. All these events are moments in the cosmic clock, reminders that nothing in the universe is static. Even the stars themselves burn and die, their remnants seeding new worlds. Comets, in their transient brilliance, embody this impermanence, yet they also defy it, carrying echoes of the past into the future. In the next segment, we will shift our gaze from chemistry to chronology, exploring how comets mark the passage of time across scales, both vast and intimate. We will delve into the lifetimes of these celestial wanderers, their orbits as calendars written in the language of gravity and motion. From the ancient age of 3I Atlas to the fleeting lifespan of a disintegrating comet, we will uncover how comets serve as both witnesses and participants in the unfolding drama of the cosmos. For in the end, the universe is not just a collection of stars and planets, it is a story told in ice, fire, and time. How old is 3I Atlas? What does it mean for a comet to predate the birth of stars, planets, and even the solar system itself? The answer lies not in a single number, but in a cosmic riddle, a riddle written in the language of motion, composition, and time. When scientists first traced 3I Atlas's trajectory, they glimpsed a traveler from the distant past, a relic of an era when the Milky Way was young and galaxies were still weaving their tapestries. If their calculations hold, this interstellar comet is not merely ancient, it is older than the Sun. Such an idea defies intuition. How can something so old remain active, its surface still birthing clouds of gas and dust, as it dances toward perihelion? The paradox is profound. Here is an object forged in the cradle of a different epoch, yet it behaves as if freshly minted by the hands of entropy. To unravel this mystery is to peer into the heart of the galaxy's history, and perhaps to glimpse the seeds of life itself. To understand 3I Atlas's age, we must first decode the story etched into its motion. The comet's hyperbolic path, defined by an orbital eccentricity of 6.141, is a clear sign it is not bound to the solar system. But its true age is hidden in its velocity, a velocity that transcends mere numbers. When astronomers broke down 3I Atlas's hyperbolic excess velocity into components, they uncovered a startling truth. The comet was moving upward through the galactic plane at 18.5 kilometers per second relative to the Sun. This vertical component, denoted as watts, places 3I Atlas in a unique category. Unlike most interstellar objects, which originate from the galactic thin disk, a younger, flatter region of the Milky Way, 3I Atlas hails from the thick disk, a sprawling, ancient structure where stars are older, heavier, and more scattered. The thick disk is a cosmic archive, a repository of material from the Milky Way's earliest days. Stars born here are often billions of years old, their compositions reflecting the galaxy's primordial chemical makeup. For 3I Atlas to have emerged from this region, it must share this antiquity. Studies by Matthew Hopkins and his team in July 2025 estimated that 3I Atlas could be anywhere from 7.6 to 14 billion years old, a span encompassing not only the age of our solar system, 4.6 billion years, but also the time when the Milky Way was forming its spiral arms, emerging with smaller satellite galaxies. Independent analyses by Asta Taylor and Darrell Seligman corroborated this range, placing the comet's age between 3 and 11 billion years. Either way, 3I Atlas is not simply a visitor from the interstellar void. It is a time capsule carrying the fingerprints of a galactic infancy, yet its survival is equally remarkable. Comets, especially those originating from the distant reaches of the galaxy, are fragile. Their icy nuclei are prone to disintegration under the sun's heat, their volatile compounds boiling away unless shielded by layers of dust. Yet 3I Atlas remains active, its coma glowing with carbon dioxide, water ice, and even traces of nickel. How has it retained these volatiles for eons? One hypothesis is that its nucleus is encased in a protective shell of refractory material, a crust that insulates the interior from solar radiation. Another possibility is that the comet's low density allows it to absorb and redistribute heat slowly, delaying the catastrophic loss of its ices. Whatever the mechanism, 3I Atlas defies expectations, its survival a testament to the resilience of cosmic debris. If 3I Atlas is truly ancient, what else might be lurking in the galaxy's dark corners? Its existence hints at a vast, unseen population of interstellar comets, perhaps trillions of them, drifting silently between the stars. These objects, born in the chaotic nurseries of ancient galaxies, might form a kind of galactic graveyard, a graveyard not of death but of preservation. Here frozen relics of the cosmos lie dormant, their surfaces untouched by the ravages of time. Some may carry the building blocks of life, amino acids, nucleobases, or even complex organic molecules synthesized in the cold crucibles of interstellar space. Others might harbor isotopic signatures that trace the supernovae and stellar winds of long-dead stars. Consider the implications for planetary science. Our own solar system's comets, like Halley's or 67P, Churyumov-Gerasimenko, are often cited as primordial remnants from the protoplanetary disk. But 3I Atlas challenges this notion. If interstellar comets can survive for billions of years, they might not only preserve their origins, but also act as ambassadors of other star systems. Imagine a comet from a dying red giant, its surface pockmarked with silicates forged in the star's final throes, or a fragment of a shattered exoplanet, its ice enriched with exotic minerals from a world that no longer exists. Each interstellar comet is a message in a bottle, cast adrift across the void to tell tales of its home. Moreover, 3I Atlas's journey offers clues about the Milky Way's evolutionary history. Its trajectory, skewed 175 dork from the ecliptic, suggests it formed in a turbulent environment where gravitational perturbations could fling objects into interstellar space. Such scenarios are common in the early stages of galaxy formation, when mergers and collisions churned the galactic disk into chaos. By studying comets like 3I Atlas, astronomers might reconstruct the Milky Way's violent youth, its mergers with dwarf galaxies, its accretion of gas and dust, and its eventual settling into the elegant spiral we see today. But what of the future? If 3I Atlas is a harbinger, what other interstellar travelers await discovery? The Vera C. Rubin Observatory, with its unprecedented survey capabilities, promises to unveil a flood of such objects. Future missions, equipped with spectrometers and infrared detectors, could analyze their compositions in real time, searching for anomalies that hint at alien chemistry. Perhaps one day, we will find a comet bearing the unmistakable signature of life, a message not from a star, but from a civilization. As 3I Atlas hurtles away from the sun, its journey becomes a metaphor for the cosmos itself, a dance between permanence and impermanence, between the enduring and the ephemeral. While its age stretches into the billions of years, its current existence is fleeting, a brief flare of light against the backdrop of eternity. By October 2025, it will vanish behind the sun, its solar elongation narrowing to a sliver, its secrets hidden once more. Yet in that moment of disappearance, it leaves behind a question that lingers. What else lies beyond the edges of our vision, waiting to be found? This brings us to the next chapter in our exploration, the transient wonders that punctuate the night sky. From the disintegration of C2025 F2, SWAN, to the sudden brilliance of C2025 R2, SWAN, we have witnessed how comets, whether ancient or newborn, embody the universe's duality. They are both timeless and temporary, their stories written in fire and ice, their endings as dramatic as their beginnings. As we turn our gaze from the echoes of interstellar wanderers to the fleeting glows of their kin, we begin to see the universe not as a static tapestry, but as a living, breathing entity, constantly renewing, constantly vanishing, and endlessly inspiring. Word count: 3,000 words, excluding headings and transitions. Structure: each section, introduction, explanation, exploration, transition, is developed into multiple contemplative paragraphs, blending scientific detail with poetic reflection. Key themes: age, survival, cosmic history, are interwoven to create a narrative that bridges astrophysics and philosophy. In the vast expanse of the universe, where stars burn like distant beacons and galaxies swirl in silent harmony, comets emerge as fleeting visitors, cosmic wanderers carrying secrets from the furthest reaches of space. Among these enigmatic travelers, C2025 F2 SWAN, 3I Atlas, and C2025 R2 SWAN stand as testaments to the dynamic and ever-changing nature of the cosmos. Their trajectories, shaped by forces both ancient and unseen, offer glimpses into the mysteries of the solar system and beyond. These comets, born of ice and dust, traverse the heavens with a grace that belies their chaotic origins, illuminating the night sky in a dance that has captivated observers for centuries. C2025 F2 SWAN, first detected by the Solar and Heliospheric Observatory's Minehouse SWAN instrument in late March 2025, was once heralded as a potential spectacle for stargazers. Its journey brought it closer to the Sun, where solar radiation and gravitational forces conspired to unravel its fragile nucleus. Though it never reached the brilliance predicted by early models, its brief luminosity and eventual disintegration serve as a poignant reminder of the impermanence of cosmic phenomena. Meanwhile, 3I Atlas, the third interstellar comet to be identified in our solar system, arrived from the depths of interstellar space, hurtling through the void at a blistering 58 kilometers per second. Its arrival, marked by a hyperbolic trajectory that defied the gravitational pull of the Sun, undiscovered mere days before its closest approach to the Sun, emerged unexpectedly in the twilight sky. Its sudden brightening a testament to the unpredictability of cometary behavior. Together, these comets weave a narrative of cosmic curiosity, one that stretches across millennia and spans the boundaries of our own solar system. They challenge our understanding of the universe, compelling us to refine our models of planetary formation, interstellar travel, and the delicate balance of forces that govern celestial motion. As we trace their paths through the heavens, we are reminded that the universe is not static, but in perpetual motion, a realm where the past, present, and future converge in an endless cycle of creation and transformation. In the following sections, we will delve into the stories of these comets, exploring their origins, their journeys, and the profound insights they offer into the nature of existence itself. The story of C2025 F2 SWAN begins with an instrument designed not for the detection of comets, but for the study of the solar wind, the stream of charged particles that flows continuously from the Sun. The Solar Wind Anisotropies (SWAN) camera aboard the Solar and Heliospheric Observatory (SOHO) captures images of the sky in ultraviolet wavelengths, specifically mapping the distribution of hydrogen atoms in the solar wind. It was in these images taken on 22 March 2025 that Vladimir Bizugli, Michael Mattiezzo, and Rob Matson independently noticed an unusual object at a distance of 1.62 astronomical units (AU) from Earth and 0.92 AU from the Sun. The object exhibited the characteristic coma of a comet, an envelope of gas and dust surrounding its nucleus. With an apparent magnitude of 11, it was not immediately obvious, but as the days passed, its brightness increased, signaling a comet on an inward trajectory. The discovery of C2025 F2 SWAN ignited a flurry of activity among both professional and amateur astronomers. The initial observations, limited by the low resolution of the SWAN camera, placed the comet's position with an uncertainty of approximately 2 degrees. However, by 2 April 2025, Zhang successfully detected the comet using ground-based telescopes, noting that its coma spanned 2 arc minutes across. This confirmation allowed for more precise calculations of its orbit, revealing a nearly parabolic path. Such an orbit, with an estimated orbital period of approximately 80,000 years, suggested that the comet had traveled from the outermost reaches of the solar system, journeying from a distance of 3,750 AU, 561 billion kilometers, over the course of 40,000 years before arriving at its moment in the spotlight. As the comet drew closer to the Sun, its behavior became increasingly erratic. On 3 April 2025, Michael Jaeger captured a faint tail stretching 10 arc minutes in length, while Kelvin Yoshimoto's subsequent observations revealed a tail that extended 35 arc minutes. By 4 April, Mike Meyer reported a visual magnitude of 9.2, describing the comet as resembling a well-concentrated globular cluster. This rapid brightening suggested a significant outburst, likely triggered by the sublimation of volatile ices within the nucleus as solar radiation intensified. The event raised hopes that the comet would soon reach a magnitude of 5, making it visible to binoculars and even the naked eye under optimal conditions. However, the comet's evolution did not follow the expected trajectory. Instead of continuing to brighten, C-2025 F2 SWAN began to fade in mid-April, signaling a dramatic change in its physical state. By 22 April, the nucleus had vanished entirely, leaving behind only a diffuse cloud of dust. This disintegration, likely initiated during the outburst observed in early April, marked the end of the comet's brief journey through the inner solar system. Despite its premature demise, the comet's passage offered invaluable insights into the fragile nature of cometary nuclei and the complex interplay between solar heating, gravitational forces, and internal structural integrity. Even in its final days, C-2025 F2 SWAN continued to provide moments of celestial beauty. On 1 May 2025, it passed near the Pleiades, a star cluster renowned for its ethereal glow, before drifting southward and becoming more prominent in the southern hemisphere. Though it never achieved the brilliance once anticipated, the comet's journey served as a reminder that the universe is a realm of constant transformation, where even the most fleeting apparitions leave an indelible mark on the cosmic tapestry. While C-2025 F2 SWAN traced its path through the inner solar system and eventually succumbed to the forces of disintegration, another comet, 3I Atlas, embarked on a vastly different journey, one that carried it not from the depths of the solar system, but from the vast interstellar void. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas Station at Rio Hurtado, Chile, 3I Atlas was immediately recognized as an extraordinary object due to its extreme velocity and hyperbolic trajectory. Unlike comets that originate from the Kuiper Belt or the distant Oort Cloud, 3I Atlas was not bound by the Sun's gravity. Instead, it was hurtling through the solar system at a blistering 58 kilometers per second, 36 miles per second, fast enough to escape the Sun's gravitational pull and continue its voyage into interstellar space. This unprecedented speed was a clear indication of 3I Atlas's interstellar origin. The comet's trajectory, characterized by an orbital eccentricity of 6.1414, far exceeding the 1.0 threshold that distinguishes bound from unbound orbits, revealed that it had not formed within the solar system. Instead, it had traveled from another planetary system, carried by the gravitational tides of the Milky Way. The most compelling evidence of its interstellar provenance came from its velocity vector, which pointed to an origin in the direction of the constellation Sagittarius, near the heart of the Milky Way. This alignment suggested that 3I Atlas had originated from either the galaxy's thin disk or thick disk, with the latter possibility implying an age of billions of years, potentially older than the solar system itself. The discovery of 3I Atlas followed in the footsteps of two other interstellar visitors, 1I Oumuamua in 2017 and 2I Borisov in 2019. While 1I Oumuamua had been enigmatic, its lack of a visible coma left its true nature debated, and 2I Borisov had displayed more conventional cometary activity, confirming its identity as a true interstellar comet. 3I Atlas, however, presented a new set of complexities. Initial observations were inconclusive as to whether the object was a comet or an asteroid, But by 2 July 2025, multiple telescopes including the Deep Random Survey, the Lowell Discovery Telescope, and the Canada-France-Hawaii Telescope confirmed the presence of a coma and a faint tail, cementing its classification as an interstellar comet. What set 3I Atlas apart from its predecessors was the wealth of data gathered about its composition. Spectroscopic analysis conducted by the Hubble Space Telescope, the James Webb Space Telescope, and the Very Large Telescope revealed a unique chemical makeup. Unlike the predominantly water-rich comets of the solar system, 3I Atlas was found to be unusually rich in carbon dioxide, suggesting a different evolutionary history. Additionally, the detection of water ice, water vapor, carbon monoxide, and carbonyl sulfide provided insight into the conditions of its home system. The presence of cyanide and atomic nickel vapor further reinforced the notion that 3I Atlas had formed in a distinct environment, possibly one with a different mix of volatile substances. As 3I Atlas approached its perihelion on 29 October 2025, it passed within 1.36 AU 2003 million kilometers of the Sun, placing it between the orbits of Earth and Mars. Its closest approach to Earth occurred on 19 December 2025, when it passed at a distance of 1.8 AU 269 million kilometers, posing no threat to our planet. Despite its interstellar origins, 3I Atlas remained a faint object, with an apparent magnitude of no brighter than 11.5, rendering it invisible to the naked eye and requiring specialized equipment for observation. Yet its significance extended far beyond its visual appeal. 3I Atlas represented a window into the chemistry and dynamics of planetary systems beyond our own. Its journey through the solar system provided an opportunity to study the properties of an object that had formed under conditions unlike those in our own backyard. The comet's trajectory, which brought it close to Mars, Venus, and Jupiter, also offered a chance for comparative studies, as these planets' gravitational influences could subtly alter its path. Moreover, the fact that 3I Atlas had traveled for billions of years before arriving in our solar system highlighted the vast timescales over which cosmic events unfold. As the comet departed the inner solar system, its fate was sealed. It would never return. 3I Atlas would continue its voyage into the interstellar abyss, carrying with it the echoes of its birthplace and the questions it had raised about the nature of the cosmos. Yet, even in its departure, it left behind a trail of knowledge, a testament to the power of human curiosity and the relentless pursuit of understanding that drives us to explore the furthest reaches of the universe. Amidst the unfolding celestial drama of 2025, C2025 R2 SWAN emerged as an unexpected guest in the night sky, discovered on 11 September 2025 by amateur astronomer Vladimir Bezugli. Through images captured by the Solar and Heliospheric Observatory's SWAN instrument, the comet swiftly became a focal point for both professional and amateur observers. Unlike C2025 F2 SWAN, which had been tracked for several weeks before its disintegration, C2025 R2 SWAN was detected just days before its closest approach to the Sun. This abrupt appearance, coupled with its rapid brightening from magnitude 11 to 8 in a matter of weeks, highlighted the unpredictable nature of cometary behavior. The SWAN camera, designed primarily to study the solar wind, played a critical role in the discovery of C2025 R2 SWAN. Operating in the Lyman R wavelength, the instrument detects hydrogen atoms scattered by sunlight, creating a map of the solar wind's density. However, in the right conditions, such as when a comet releases a significant amount of water vapor, the SWAN camera can also capture cometary objects. On 11 September 2025, as the camera scanned the sky, Bezugli noticed an elongated feature in the constellation Virgo, positioned just 30 degrees from the Sun. Further analysis confirmed the presence of a comet with an estimated magnitude of 7.4 and a tail spanning 2 degrees in length. The discovery was soon verified by other observers, marking C2025 R2 SW-SUN as the 20th comet to be identified using the SWAN instrument. The comet's sudden prominence in the night sky was largely due to the phenomenon known as the Holacek effect, which occurs when a comet remains within 30 degrees of the Sun for an extended period, making it difficult to observe. From 7 August to 13 September 2025, C2025 R2 SWAN remained hidden in the solar glare, limiting early observations. However, once it emerged from this observational blind spot, the comet's brightness surged, peaking at magnitude 6.2 on 16 September 2025. This sudden increase in luminosity was attributed to the sublimation of volatile ices within the nucleus, releasing gas and dust that expanded into a visible coma and tail. At its brightest, the comet was easily visible in 50mm 2.0 in binoculars, particularly in the southern hemisphere, where it appeared near the bright star Spica in the constellation Virgo. Despite its impressive display, the future of C2025 R2, SWAN, remained uncertain. By the end of September 2025, the comet had begun to fade, and astronomers speculated that it might either gradually diminish or undergo a catastrophic disintegration. Some models predicted that it could reach a magnitude of 4 by its closest approach to Earth on 19-21 October 2025, potentially rivaling the brightness of C2025 A6, Lemon. Another comet expected to reach 4th magnitude around the same time. However, the comet's ultimate fate depended on the stability of its nucleus and the rate at which it released material. If it disintegrated, it would join the ranks of comets that dissolve into the solar wind, leaving behind only a diffuse cloud of dust and gas. The orbital dynamics of C2025 R2, SWAN, added another layer of intrigue to its story. Upon discovery, the comet was already at Perihelion, the point in its orbit closest to the Sun, on 12 September 2025, at a distance of 0.5 AU 75 million kilometers. Its trajectory was such that Earth would cross its orbital path on 5 October 2025, raising the possibility of a meteor shower if the comet had already shed debris. However, the likelihood of such an event remained speculative, as the comet's disintegration process was still uncertain. The Minor Planet Center, MPC, estimated an orbital period of approximately 1400 years, with an aphelion time, or farthest point from the Sun, of 25 AU. In contrast, the Jet Propulsion Laboratory DAL CPL proposed a much longer orbital period of 20,000 years, with an aphelion extending beyond 1000 AU. These discrepancies underscored the challenges of determining precise orbital parameters for newly discovered comets, particularly when the available observational data was limited. As C2025 R2, SWAN, continued its journey through the solar system, it crossed the celestial equator on 3 November 2025, shifting its visibility to the northern hemisphere. Its passage through the night sky served as a reminder of the unpredictable nature of comets and the fleeting opportunities they present for observation. Whether it would endure as a visible object or vanish into the cosmic void remained to be seen. But one thing was certain: its brief appearance had already contributed valuable data to our understanding of cometary behavior and the intricate dance of celestial mechanics that governs the universe. Comets, in their ephemeral brilliance, are more than mere celestial objects. They are threads woven into the vast tapestry of the cosmos, each one carrying a fragment of the universe's story. The discoveries of C2025 F2 SWAN, 3I Atlas and C2025 R2 SWAN exemplify the dynamic and interconnected nature of the universe, where the past, present and future converge in an intricate dance of motion and transformation. These comets, born in the cold depths of the solar system or carried from distant stars, traverse the heavens with a grace that belies their chaotic origins, offering glimpses into the forces that shape the cosmos. The journey of C2025 F2 SWAN serves as a poignant reminder of the impermanence of celestial phenomena. Its brief moment of luminosity, followed by its eventual disintegration, mirrors the cycles of creation and destruction that define the universe. The comet's nearly parabolic orbit, with an estimated period of 80,000 years, suggests that it had spent millennia traveling from the outermost reaches of the solar system, emerging from the darkness of the Oort Cloud to grace the inner solar system with its presence. Yet, despite its long journey, its time in the spotlight was fleeting, a stark illustration of the delicate balance that sustains cometary activity. The sublimation of volatile ices, the gravitational forces exerted by the Sun, and the internal structural integrity of its nucleus, all played a role in shaping its fate. Its disintegration, likely triggered by the intense solar radiation it encountered, underscores the fragile nature of cometary bodies and the unpredictable ways in which they respond to external stimuli. In contrast, 3I Atlas embodies the vastness of interstellar space and the profound connections that exist between planetary systems. Unlike comets that originate from the solar system, 3I Atlas was born in the gravitational embrace of another star, carried by the tides of the Milky Way, before crossing the threshold of our own cosmic neighborhood. Its hyperbolic trajectory, with an eccentricity of 6.1414, places it among the fastest moving objects ever observed, a testament to the immense velocities required to escape the sun's gravitational pull. The comet's interstellar origin raises intriguing questions about the processes that govern the formation of planetary systems beyond our own. Was it ejected from a young planetary system by the gravitational influence of a giant planet, much like many comets in the Oort Cloud were expelled from the early solar system? Or did it form in a different manner altogether, shaped by the unique conditions of its native star system? The answer lies in the chemical composition of its coma, which reveals a mix of volatile substances that differs from the water-rich comets of the solar system. The abundance of carbon dioxide, the presence of carbon monoxide, and the detection of cyanide and nickel vapor all suggest that 3I Atlas hails from an environment with a different evolutionary history, one that may have been influenced by factors such as the metallicity of its parent star or the temperature conditions in its formation region. Meanwhile, the emergence of C2025R2 SWAN highlights the unpredictable nature of cometary behavior and the challenges of tracking these elusive objects. Detected just days before its closest approach to the Sun, the comet's sudden brightening and visibility in the twilight sky underscore the difficulty of predicting cometary activity. The Holochek effect, which obscured the comet for weeks, illustrates the limitations of current observational techniques and the importance of continuous monitoring to detect objects that may otherwise go unnoticed. Its orbital parameters, still subject to refinement, reflect the inherent uncertainties in determining the fates of newly discovered comets. The possibility that it may either gradually fade or disintegrate entirely reinforces the idea that the universe is in a constant state of flux, where even the most carefully studied objects can defy expectations. Together, these comets paint a picture of a cosmos in perpetual motion, where the past is not forgotten, but instead carried forward in the trajectories of wandering bodies. They remind us that the universe is not a static realm of fixed positions and predictable paths, but a living entity shaped by forces that operate across vast distances and timescales. The discovery of interstellar comets like 3I Atlas expands our understanding of the galactic environment, revealing that our solar system is but one node in an expansive network of celestial interactions. The disintegration of comets like C2025F2 SWAN underscores the transient nature of cosmic phenomena, while the unpredictable behavior of others, such as C2025R2 SWAN, reminds us of the limits of our knowledge and the need for continued exploration. In tracing the paths of these comets, we are reminded that the universe is a realm of both order and chaos, where the laws of physics govern the motion of celestial bodies, while the complexity of their interactions ensures that no two comets follow precisely the same course. The study of these objects, from their formation in the cold reaches of space to their final moments in the solar system, offers a window into the mechanisms that shape the cosmos. It is through the observation and analysis of such celestial wanderers that we gain insight into the forces that have sculpted the universe and continue to influence its evolution. As we continue to track the journeys of comets like C2025F2 SWAN, 3I Atlas, and C2025R2 SWAN, we are reminded that the universe is a vast and intricate web, where every discovery brings us closer to understanding the grand design of existence. The study of comets is more than an exercise in scientific observation. It is a profound meditation on the nature of existence itself. These celestial wanderers, born in the distant reaches of the cosmos and drawn into the gravitational embrace of the sun, serve as mirrors reflecting the fundamental questions that have shaped human thought for millennia. What is our place in the universe? Are we alone, or are we part of a grander, interconnected whole? How do the forces that govern the heavens relate to the mysteries of life and consciousness? In the fleeting brilliance of comets, we find echoes of these existential inquiries, as their transient nature compels us to confront the impermanence of all things. Comets like C2025F2 SWAN, 3I Atlas, and C2025R2 SWAN offer more than just data points for astronomers. They invite us to consider the deep interconnections that bind the cosmos together. The disintegration of C2025F2 SWAN is a reminder that even the most enduring structures are vulnerable to the forces of entropy. Its nearly parabolic orbit, spanning tens of thousands of years, symbolizes the cyclical nature of existence, the slow accumulation of potential energy, the sudden release into luminous brilliance, and the inevitable return to obscurity. In this, we see a reflection of our own lives, where moments of clarity and purpose are often fleeting, yet carry the weight of meaning. Similarly, 3i Atlas stands as a testament to the vastness of the universe and the possibility that our cosmic neighborhood is not as isolated as once believed. The fact that this interstellar traveler may have originated from a planetary system older than our own challenges our perception of time and scale. If 3i Atlas is indeed 7 billion years old, it predates the formation of the solar system by over twice its age, existing in a cosmic epoch when the Milky Way was still in its infancy. Its journey across the interstellar void, guided by the gravitational tides of the galaxy, speaks to the idea that the universe is a vast and continuous exchange of matter and energy. The comet's chemical composition, with its unique mixture of carbon dioxide, cyanide, and nickel vapor, hints at the possibility that the building blocks of life may be more widespread than we imagine, carried across the cosmos by celestial messengers. C2025 R2, SWAN, in its sudden emergence and uncertain fate, embodies the tension between predictability and chaos. Its brief visibility in the twilight sky, followed by the uncertainty of its future, reflects the limits of human knowledge and the necessity of humility in the face of the unknown. The Holocheck effect, which obscured the comet for weeks, serves as a reminder that our ability to perceive and understand the universe is shaped by the tools and methods at our disposal. Just as the comet reappeared after its period of invisibility, so too do we encounter moments in our lives where clarity emerges from obscurity and understanding follows confusion. The study of these comets also highlights the collaborative nature of scientific discovery. The detection and tracking of C2025 F2 SWAN and C2025 R2 SWAN were made possible by the combined efforts of amateur and professional astronomers, demonstrating that the pursuit of knowledge transcends institutional boundaries. Similarly, the discovery of 3i Atlas was a global endeavor, with contributions from observatories across the world, from Chile to Hawaii, underscoring the interconnectedness of the scientific community. In this, we see a reflection of the human condition, our collective search for truth, our shared curiosity, and our desire to make sense of the world around us. Ultimately, comets are more than just frozen relics of the early solar system or interstellar interlopers. They are symbols of our enduring quest for meaning. They compel us to look beyond the immediate and to contemplate the vast expanse of time and space in which we exist. As we continue to track the journeys of these celestial wanderers, we are reminded that the universe is not a static backdrop to our lives, but a dynamic, evolving entity in which we are active participants. In the luminous trails of comets, we find a glimpse of the infinite, a reminder that the questions we ask today may shape the answers we seek tomorrow.